All right, calculus, we're looking at implicit, to imply, not exply, or be explicit. We're not being direct, we're kind of using indirect means to kind of get to a derivative here. That's the general idea, indirect, not direct, indirect. So first, let's kind of brute force something that is direct. We look at this function, x squared plus y squared, whoa, that's different. Y squared. Not y, but y squared. Something happening to y as well as x. So this is how that plays out. The general idea is that if there's something else happening to y and x, then we have this relationship. We have an equal sign implying some type of relationship between values and things. But it's not exact. It's not y equals. It's not you do your thing and then I will be dependent on you. That's why we call y a dependent variable often. And x is independent, where it kind of does its input, but then a lot of stuff happens to it, and then the y is dependent on what happened to x. This is more indirect. So let's deal with it slightly different. Let's make it look direct. So if I were to make it look direct, one step I could do is move x squared over to the other side. That would give me y squared equals 25 minus x squared. Then I would have y equals square root of 25 minus x squared, which is really 25 minus x squared, all raised to the 1/2 power. That being said, I could take the derivative of this one. This is a direct explicit type function that we've been able to deal with. Y prime here would be 1/2 25 minus x squared to the negative 1/2, and then we'd multiply that by the derivative of the inside, which in this case would be negative 2x. Now, it does have a problem because there's a little bit of ambiguity in here. In this square root part of the result, is it the positive square root or is it the negative? We don't know. We don't know. We'd need more information. It's not really determined. So that's explicit differentiation. What we're going to be looking at is an implicit differentiation. And the idea with that has a lot more to do with what is the derivative of y anyways. So when you think about y equals some function of x, then we take the derivative of both sides, and over here we got, let's say this was x squared. Then the derivative would be 2x. And over here the derivative of y we call dy dx, or y prime. Then we're going to treat this like a chain rule. What that means is that when we start with x squared plus, now this y is going to be kind of a chain here. I'm going to take the derivative of each term individually, but we're going to have something going on with this inside piece here. So we take the derivative of x squared, that's just 2x. And then the derivative of this next one, we drop the 2, subtract 1 from the power, and then we leave the y alone, but then we're going to multiply by the derivative of y. And the key thing is to remember that the derivative of y, you kind of put this together. If you look at it, it looks a lot like dy dx. Now we're going to stick with dy dx as the format, the notation. Why? Because y primed equals a lot, or looks a lot like y to the first. In fact, wait, is that y to the first equals y primed? Or y prime, I don't know. Again, ambiguity is not our friend. We want more specific detail. So I just took a chain rule here. I took the derivative of the outside, but I got to multiply by the inside. The inside would have been dy dx equals 0. Now, this is all cool and stuff. I did the derivative all over the place. But I want to simplify it and get that dy dx by itself. So anything that's not dy dx, in other words, like a non-dy dx, would be this term here, the 2x. I'm going to move that over. So that would give me 2y dy dx equals negative 2x. Then if I were to divide by 2y on both sides, I'd have dy dx all by itself, perfect, and negative 2x over 2y, or simplified even more, negative x over y. That actually wasn't that bad, as long as I remember this, that it's a chain rule, and that the derivative of y with respect to x is called dy dx. Well, let's keep using that idea. So we look at this one here, and it's very similar. Notice it's nearly identical. Actually, hang on. What we wanted to find the slope of the tangent line. I took the derivative, I found it, but then I need to find it at a specific point. Dy dx at, in this case, x equals 4 and y equals 3 is going to be negative 4 over 3. Oh, well, that was easy. Especially once I had it in a very general format. Okay, so we got this for the most part. One thing to note here is if we were to do it with x the same way that we were to do it with y, notice this right here, we'd get the dx dx. And dx dx is just 1. The derivative of x with respect to x is 1. We've kind of defined that earlier, but even more specifically, look at this. It just kind of makes sense algebraically too. So we don't really need that. This next one, find dy dx for x squared minus y squared at 5 negative 3. At 5 negative 3, that means we got to also plug that in. So let's do this. We got 3 terms here. The derivative of the first term is 2x. The derivative of the next term is negative 2 times y to the first power times dy dx. So notice that what's happening here, we got equals 0 on the other side, by the way. Notice what's happening here is that every time you take the derivative of a y, you're going to multiply by dy dx. That's interesting. Okay, so if we were to simplify this one, it would be a lot like the other one. I've already done that once, so we're just going to cheat and kind of use what we know. It's going to be negative x over, wait a second, this is negative 2y. So that's going to wind up being a negative y down there, or just x over y. Then that means that dy dx at this point, 5 negative 3, is really equal to 5 over negative 3. Well, that's almost too easy. All right, let's look at this next one. Change color. Why? For fun. We got a product rule, a and b, and then we got this y here that's going to have a dy dx in it as well. So let's do this product rule. Remember that the product rule is a, or derivative of 1 times the original of the other, plus the flip-flop of that, vice versa. So that means we're going to have x times the derivative of y, which is dy dx. That's kind of weird. The dy dx is times x. Why? Because we took the derivative of y with respect to x. Plus b times a prime, which is going to be y times the derivative of x, which is just 1. Plus, what's the derivative of y? Well, it's the derivative of y with respect to x equals 0. All right, so let's take this one step at a time. First, I'm going to move this non-dy dx term over here. That means I would have x times dy dx plus 1 times dy dx equals negative y. Now, something to keep in mind here, you can treat this dy dx somewhat like just any other algebraic piece of the term. Because both of these terms have it in common, I can actually factor that out. And I want to factor that out. That's going to be a general step in this process. Once we've moved when we're solving for dy dx, you move all the non-dy dx terms like we did here, moving this over. Then we're going to factor out that dy dx. We'd be left with x plus 1 equals negative y. But then to get this dy dx all by itself, I got to divide by whatever that leftover was. So in this case, x plus 1 over x plus 1 simplifies. We're trying to calculate the slope at 2, 3. So that means dy dx at 2, 3 is going to be a negative 3 on top over 2 plus 1 on bottom, or negative 3 over 3, or negative 1. Any one of those would have been correct. This is the free response level. This is the multiple choice level. Easy, super easy. Let's do some more. We'll probably take a break after this page just to keep us kind of fresh. All right, so this next one, again, we got product rule and another product rule. So let's call, and then on the other side, we got some left over as well. Let's call this A and B, and then C and D. So we need lots of space here. We're going to have AB prime plus BA prime plus CD prime plus DC prime equals, what happens on the other side? It's going to be a 2. So let's focus on the first term, AB prime. That's going to be x squared times the derivative of y to the first power, or in other words, dy dx, plus BA prime. That's going to have a y times the derivative of x squared is just 2x, plus CD prime. C is x. The derivative of d is going to be 2y dy dx, plus DC prime. D is y squared, and the derivative of c is x. The derivative of x is just 1. And we still have equals 2. Okay, so I notice here that I have this term and this term. The first and third terms have dy dx, but the other two don't. So I'm going to move those over. That's going to give me x squared times dy dx plus x, 2xy, I guess you could say, times dy dx equals 2 minus 2xy minus y squared. Now again, we got to factor out this dy dx. We'll be left with x squared plus 2xy. We're going to wind up dividing by that. We have 2 minus 2xy minus y squared. So we're going to divide by x squared plus 2xy on both sides. Now I know this seems like a lot, but even after we've done all that, we still have to figure out the slope at 1, 1. So I'm going to encroach a little bit here on example 4, but we should be okay. 1, 1 is going to be 2 minus 2 times 1 is just 2. So that's actually 0. Then minus 1 squared. So those make a 0. Then on the bottom we have 1 squared plus 2 times 1, or just 2. So this is going to equal negative 1 on top over 3 on bottom. That is your slope of this equation at this point. All right, let's do another one. Differentiate some color here. Let's go for red. So we got dy dx, and this is our stuff. So we have y plus, this is going to be xy to the 1/2. And that might look kind of complicated as a chain rule, but let's do some more simplifying. I'm going to say y plus x to the 1/2, y to the 1/2 equals 4. You can distribute a power when all the terms inside are being multiplied. That's awesome. Now we just have a product rule. So we're going to have the derivative of the first term is just dy dx. Now we have this a and b function. So plus ab prime, so x to the 1/2 times negative 1/2, or pardon me, 1/2 space a little bit here. B prime is going to be 1/2 times y to the negative 1/2. But we took a derivative of y just now, so we got to multiply by dy dx. Plus, now we got the next piece, b a prime. Well, b is just y to the 1/2. The derivative of x to the 1/2 is going to be 1/2 x to the negative 1/2. And all of that equals 0. Wow, that's a lot. Notice here that I got dy dx times 1 and dy dx times all of this, but I need to move this other piece, y to the 1/2 times 1/2 x to the negative 1/2 over to the other side. So let's do that. We'll pretty much just change the equal sign over here. So we got negative y to the 1/2 times x to the negative 1/2. And this is really negative 1 over 2, negative 1/2. Then on this side, we have dy dx times a 1, because this is a 1 here, plus this other piece here, x to the 1/2 times 1/2 y to the negative 1/2. Wow, that's getting big and sloppy. Let's go and divide by that on both sides. That would give us, if we work this out here, 1/2 y to the negative 1/2, and then we're going to divide by that on this side, 1 plus x to the 1/2 times 1/2 y to the negative 1/2. Wow, that looks complex. So what you would do essentially here is plug in 2 and 2 and then evaluate. Just for time's sake, I'm going to go ahead and leave that till later. Well, you know what? No, let's go ahead and work it out. For the numerator, we have a y to the 1/2 times x to the negative 1/2. Now, this is interesting, because when you have a negative power here, right there, that means it's going to be in the denominator. And you got to notice here that x equals y. So whatever I plug in for x, I'm also plugging in for y. And if I evaluate here y to the 1/2 times x to the negative 1/2, that's the same thing as saying y to the 1/2 times y to the negative 1/2, which means that those two terms kind of cancel each other out. So we have a negative 1/2 on top. So this is going to equal negative 1/2 divided by, let's see what we'd have on bottom, 1 plus, well again we have this x to the 1/2 times y to the negative 1/2. So those are going to simplify each other out. It's going to be square root of 2 over square root of 2 pretty much. So this is just going to have 1 plus 1/2. Or in other words, negative 1/2 over 3/2. Now if I were to simplify all that, what would we get? Negative 1/3. Lots of fractions and stuff going on there, but that's what you would eventually wind up doing. All right, let's look at this next one. So again, let's identify what's going to happen. We got some chain rule action going on here. There's an inside layer, or an outside layer, and then we have an inside layer here. But within the inside layer, we got this y, so it's going to be interesting seeing how that plays out, how it's a mix of y and x on the inside. Then we have this y here as well to consider. So when we take the derivative of this first term, it's going to be 2 times that inside layer to the first power. The inside layer is x plus y. The derivative of the inside layer, the derivative of x is just 1. The derivative of y with respect to x is dy dx. So that's that first chain rule. Plus, this next term, the derivative of y with respect to x is dy dx. That's how we write that. Equals the derivative of 2, which is 0. Okay, so we got some interesting things going on here. Notice that I'm going to have kind of like this multiplication of these two binomials here. So it'll be 2x, 2y, 1, and dy dx. So if I were to multiply that out, I'd have a 2x and 2y. That's pretty normal. Then I'm going to have a 2x dy dx and a 2y dy dx. So if I were to simplify that, that means I have 2x plus 2y plus 2x dy dx plus 2y dy dx. Okay, so that's that whole first part, but I haven't written this dy dx. So plus dy dx and then equals 0. Now remember, the key is kind of take the pieces that are separate those from those that are, the haves and the have-nots, I guess you could call them. That means that we'd have dy dx on this left side, and in here we have a 2x, a 2y, and a 1. So I'm going to have 2x plus 2y plus 1 equals, now when I move these other two terms over here, it'll be negative 2x, negative 2y. So then if I divide by 2x plus 2y plus 1 on both sides, 2x plus 2y plus 1. Let's see what would happen. Because I want to evaluate this at 0, 1. So that means that any x term is actually going to be a 0, so I'm just going to get rid of those. That means I would have a negative 2 on top. Then on bottom I'd have 2 times 1 plus 1, or 3. We got a lot of thirds going on in this whole worksheet, but that's okay. I guess that's not too bad. Right, let's switch back to purple, just to wrap up this page. So we got x squared plus 4y squared equals 4. This is actually pretty simple at this stage as far as how we're dealing with this, but let's see what would happen. So we take the derivative of x squared, that's just 2x. We take the derivative of 4y squared. Well, it's a chain rule, so we're going to have a 4, and we drop that 2 times y to the first. Then we do the derivative of the inside, which is dy dx, equals 0. So now if I simplify this, I see that the 2x can be moved over because it's non-dy dx. And I'd have 8y, 4 times 2 times y, times dy dx equals 2x, negative, because it moved across. So I'm going to divide by 8y on both sides. I would have dy dx equals negative x over 4y. If I were to calculate dy dx at 2, 0, that would equal negative 2 over 4 times 0. Whoa, this is where it's kind of weird. It's a number over 0. So what's really happening here? This does not exist, first of all. That means that that's not really differentiable, that we can't really take the derivative and apply it at that point. This function is not differentiable at that point. But what does that mean when you have a number over 0? What does it mean? Well, let's think about this. If you're trying to measure rise over run, that's what slope really is. If your rise has some up and down action, but your run does not, there is no run, then that means you're only rising. That means you are only vertical in your change. You're not horizontal. That means that you have a vertical tangent line. That is an interesting thing. We're going to get some more of that in the next video, but that's really interesting thing. So when you have a number over 0, it's a vertical tangent line.